You can't use a chair, you can't use props. My name is Donna Migdal, and I teach STEM to 5th and 6th graders in the Oceanside School District in New York. Justin, someone has to be there to catch it. My 5th graders are involved right now in roller coaster physics, where they have to create a roller coaster that is both fun and safe at the same time.
It was either not enough friction or too much momentum.
They're learning about potential and kinetic energy, and they're learning about Newton's 3 laws of motion, and then trying to see that at work and at play within the design challenge. Last week they tested for the safety piece to keep that marble on the track at all times, and today the objective is that the students design the optimal coaster with the longest ride so that the marble gets to the very end without falling off. So today we're going to be testing for fun. The fun that I want you to test for today is how that marble can get to the end of the track. That's the piece of fun we're trying today. All right, but I really think that good engineers learn from what they experienced and tested beforehand. So I want to do a chime and think about the greatest challenge with safety that your group had. I started today's lesson with something called chiming. They pick a chimer in each group, and they tell about what trials and tribulations they had the week before in terms of the engineering design process, and the other students take notes and then chime in.
In our group, when we connected both of the foam insulations, our marble came, and then it kind of like jumped because it was kind of falling into the crack and the indentation.
First off, it absolutely is a formative assessment tool for me to understand, to get a pulse of where the students are. And secondly, to promote autonomous learning, where students value each other's ideas, and the learning does not have to pass through me. It goes directly from student to student, and they start to honor each other's ideas, and they start to understand that they're the ones that are the true problem solvers.
I think that the marble kept falling off maybe because you need more speed. So if you do a little bit of a hill and make it down, maybe it'll gather more potential energy, so it'll have the energy to make it across the loop.
Communication is a huge part of engineering design. Otherwise, their ideas would stay to themselves. They have to communicate their ideas, and through that, they learn and they get smarter in terms of widening their ideas about how the world works and how the physics world works.
It had too little dissipated energy, so it had too much potential energy coming off the loop, and then it would just like fly off the track.
They want you to now do an individual sketch. I'm going to give you 4 minutes to do your individual sketch. Labels are important. Their individual sketches are a good way for me to assess what their ideas are, for them to do a self-assessment, and for peer assessment. You must have, if you're thinking of clothoid loops, make sure you say the word clothoid. If you're thinking of a small, medium, or large loop, you must say that. I want them to show the science that they know. When they're sketching out their idea, if there's a loop and they know that it's centripetal force, they should put centripetal force starts here. What type of loop? We learned about the difference in engineering, between clothoid and circular loops, so they should label that clothoid. If they're not sure about the exact amount of centimeters, either a medium, a short, or a long rise and run. Any ideas that you have are in that sketch, because that's your way of communicating to the rest of your group how to sell your sketch as the design of the day, the first design of the day.
So I was thinking 2 small clothoid loops, and then like a small hill after each one, and then a medium rise with a long run, so it'll have enough kinetic energy to go around in the first loop, and also tape at the end to cause friction.
I like for them to do a group sketch because it gets them involved in the engineering design process, what it's all about.
I think we used the sandpaper to slow it down at the end
Because it's like all
because
friction and rugged.
because the tape wasn't like helping that much because
really.
it wasn't that like strong.
You can't have 4 different designs in one group. You have to come to one design. We don't have the materials, we don't have the time, so they have to do a lot of team building and collaboration and come up with a consensus.
At the end, would sandpaper work? Because sandpaper and the marble rubbing together will cause friction. I did that too.
So now we're going to take your sketch, your group sketch, and we're going to go to the model simulator, and you're going to do 2 runs. When they're on the simulator, it's not just playing the game, because they can never get away from what an engineer does. Remember, everyone, that the mass that you're choosing, whether it be the small mass or the large mass, that the amount of cars you use in the simulation duplicates that idea. So if it's small mass, you're not going to use more than 2 cars. They take Post-its with them, and they take their design portfolio. They map out their sketch and design it on the program. And then if they fail, what's the failure? They write that down, like if it was stuck or if it crashed. And after that, they have to write why they think that happened, and then they have to write 1 modification.
Okay, smaller rise.
And they do the same process over again.
Like, make this straight, and then if you want to put, like, sandpaper here, like, do it like that.
They're really developing an understanding for systems thinking. So if I take one part out of the system, or I change one piece of that system, how does that affect how that system works? And that's a big idea in science, and that's realized through this design challenge. Your first initial hill, it was up, and why are you lowering it?
We wanted to lose potential energy because we had too much kinetic energy and we didn't want to crash at the end of the roller coaster.
So you're thinking the higher, the lower the rise, the less potential energy you'll gather and less energy in the system? Masking tape is now 2 for 1 today only, 2 for 1. I deliberately don't give them many materials when they start a design challenge because I believe that the more constraints, the better problem solvers they become. They have a choice of 2 marbles for this design challenge. It's a small mass and a larger mass. Why large mass and not small mass?
Because we want to store more energy.
Okay, there you go. The foam pipe insulation, 2 pieces per group, and they can buy masking tape as well. And then I throw in other materials as the inquiry grows.
2 sandpaper, 2 decimeters sandpaper,
Sandpaper.
and 1 decimeter of rubber.
Wow, you're really spending a lot of money. You have all that money?
Yeah.
Okay. Today I introduced a sandpaper strips, decimeter strips, and rubber decimeter strips. And I introduced that because the problem last week was the students were having a hard time slowing that marble down. So I decided to give them a little bit more incentive to use some of their knowledge of friction. Rubber. Why rubber and not sandpaper?
Because it seems like rubber would have more friction. And it seems more
Is it less expensive or more expensive?
less. And that's enough again.
Can I feel the rubber?
You can feel it. Feeling the material is free. Testing.
Now we have a 75-inch rose.
Okay, 75. So can somebody write that down? Robert, can you write it down?
I can write that down, no problem.
The students have assigned jobs, which is another key piece of the engineering design process. The measure is recording the rise and the run of the design that they're making when they're building the loops, also measuring the height and the width of the loops as well.
That's like the rise and the run, how many centimeters it is. So if it works, next week we can like use it again.
The role of the recorder in the process is they are writing down any ideas that they may want to capture, either a great finding and a great question, and any trade-offs and modifications.
We put tape to cause friction.
Oh, at the end, because according to Newton's fourth law of physics, the friction will cause as an unbalanced force, stopping the motion, which is the marble.
Oh, but Carolyn, like see, like the shape.
They match their learning styles or their strengths to what job they choose. And that's a good assessment piece for me, and it's a good reflection for them as well.
This way. Oh yeah, that's a smart idea.
I'm the organizer in the group, and I make sure that everyone's doing their job, that everything's recorded at the end of the day, and make sure that all the accounting's down. And I kind of keep track of who's doing what, how it runs.
Okay, maybe this is like a little too much.
First we need to do this.
You're the accountant now?
Okay.
I'm the accountant in my group, and everything that we use in our roller coaster takes money off of our balance. We started with $23.60 and we ended with $12.40 because we spent like a lot of money because we needed more materials to make our roller coaster successful.
Giving students a budget to work with a design challenge is essential because it makes them think about, well, if I'm going to buy this, what idea do I have to trade for that? And that just creates better problem solvers. It also makes them better mathematicians because they have to do real-world word problems as they are figuring out the money situation and keep a running balance, adding and subtracting and multiplying decimals.
I multiplied 27 cents times 10, and I got $2.70.
I have an idea.
And our total is decreasing, so we're down to $1.95.
What's your prediction before you go?
I think it'll
Why, do you think it's too much energy in the system?
Yeah. Because we also have like a few like
When students are involved in the engineering design process, the math and science that they're learning and applying into that design challenge kind of seamlessly come out. And with that, so do student misconceptions. What are you going to modify first? You get one modification at a time.
We have to make it so it has less energy.
Less energy. So do you think, Rebecca thinks adding a hill is going to give it less energy. So here, follow my finger. So you're going up. What are you gaining?
Potential, then you get
And
too
what-
much kinetic energy.
So does a hill take away energy from the system or add energy to the system? And that's so key to a teacher, because once you capture and have the space to really listen and see those misconceptions, the more you can then develop future lessons to deal with them. What is it gathering as it goes up?
Potential.
And what is it releasing as it goes down? So is that a fact?
Yeah.
Do you think that you're adding or taking away when you add another one?
We're adding.
But yeah, we need friction.
And one of the key pieces for STEM, for me as a teacher, is to see the students welcoming problems. You don't see that every time in the classroom. And when students can actually say, bring on the challenge, here's another problem, now let me get my toolkit of strategies together to solve this problem, that to me is immeasurable. And that is really the key in STEM, is creating lifelong problem solvers who have a problem, say, okay, now what do I have to do to modify it? How am I going to fix it? It's all about modification and making trade-offs, and working with that science and math to do that is a dream come true for a teacher.
This teaching moment is made possible by Chase.